All right, so today we're going to be looking at diagonalization uh, and powers of a matrix. And so we'll talk about what those terms mean. We'll review a little bit of what we did with finding eigenvalues and eigenvectors, and we'll see how these two things are connected. Um, so the first thing it asks us to do in the starter, it's kind of part of this investigation that you see down here. But in order to do this investigation, we have to look at this starter. So this is just reminding us what eigenvalues are and what eigenvectors are. And so it says verify that -1 and 8 are the eigenvalues for this matrix, right? So this is a case where, hey, here are the eigenvalues of this matrix. You don't need to go find them. You just need to verify that those are the eigenvalues given the corresponding eigenvectors of 1, 2, and 1, -1. And so right here it says note that it says verify, not show that. If it said show that, we'd have to do the whole process of finding them and showing that they are -1 and 8. But if it says verify, we can assume that those are correct, and we can use them to kind of verify that it is correct. So if we have this matrix A, then what should be true is if I take matrix A, which is this one, and I multiply it by my eigenvector, right? So like if I multiply it by my, we'll just take the first eigenvector and do that one first. It should be the same thing as taking my eigenvalue and multiplying it by the eigenvector. That's what we figured out, is that the transformation is the same thing as multiplying by some constant. In this case, the stretch of -1, a scale factor of -1, because that's what the eigenvalue is. And so we can do this multiplication on the left. And so this is multiplication we should be able to do by hand. We don't necessarily have to do the calculator. 5 times 1 is 5. -3 times 2 is -6, so plus a -6. And then -6 times 1 is -6. And -2 times 6 is, 2 times 2 would be +4. And so we want to see, does that actually indeed equal -1, 2? Sorry, -1 times the vector 1, 2. And so combining those, we see we get -1, -2, which is the same as this vector. If I distribute that -1, it is -1, -2. So it works for that one. So what we verified in this first part is that with an eigenvalue of -1, sorry, you have an eigenvector of 1, 2. And so we can verify the same thing for the other one. So if I take my original transformation matrix, multiply it by my eigenvector, now I'm looking at this second one, my result should be my eigenvalue times my eigenvector, right, which is that 8 is the other one. And so again, just doing multiplication of that one, 5 times 1 is 5, plus -3 times -1 is 3, -6 times 1 is -6, 2 times -1 is -2. And so we end up with, and that should equal, if I distribute the 8, it would be 8, -8. And that is true, 8, -8 is the left, 8, -8 is the right, and so that works. And so we verified that those are indeed the eigenvectors that go with those eigenvalues. So we're going to use that kind of in this investigation down here. And so in the first part, it says, let P be a matrix containing the eigenvectors of x1 and x2. Right, so P is a matrix made up of the eigenvectors, right? That's what these are, the eigenvectors. Right, and we can see that they're the same as the ones above, 1, 2, 1, -1. And there's this D, which it's D because it's a diagonal matrix, which means I have 0 in our diagonal here, and I have the eigenvalues in the diagonal over here. And so we can see that D is -1, 8, with zeros in the other diagonal. And so the first thing it says to do is find AP, right? A times P, which is going to be our matrix A, which is from above, right? If we're wondering where A is, we're taking this one up here. So it's 5, -3, -6, 2. And we're going to multiply that by 1, 1, 2, -1. Right, again, we could do this by hand or do it in the calculator. If we do it in the calculator, we're going to get -1, 8, -2, -8. All right, so that's multiplying those two together. And then, so we found AP, and it says show that AP is the same as PD. All right, so let's find what P times D is. And we are hoping that it is the same thing as -1, 8, -2, 8, -8. So P times D is 1, 1, 2, -1. That's P. D is -1, 0, 0, 8. And putting that in our calculator, we do end up getting -1, 8, -2, -8. Right, so we show that, yes, they indeed are the same, right? AP does equal PD, and we've done that first part. So part B says explain, using the definition of eigenvalues and eigenvectors, why this will always be the case. Like, why is it always true that AP times AD will always be the case when you have this kind of diagonal matrix that represents D, this P matrix, which represents the eigenvectors. Why, when I multiply those together, I kind of get the same thing. And so the reason is that we'd say from the definition of eigenvectors and eigenvalues, we have this equation that is true. If I have A and I multiply it by one of the eigenvectors, which are representing with x1, it's going to be the eigenvalue times that same eigenvector. Right? That's what it means to have an eigenvector and an eigenvalue. And we know that the same is true for a second set of values. So and A, our transformation matrix, times the second eigenvector is the same as taking the eigenvalue and multiplying it by that eigenvector. And these can just be combined. And so if I combine those two, so by combining x1 and x2 and, sorry, this should be a lambda 2. So by combining those two things, right, you get the fact that A times P is P times D. Right, it's taking these eigenvectors that were these two-dimensional vectors, x, y, and making it a 3 by 3 matrix. So we're saying x1, y1, and x2, y2. Right, that's what D is now representing. And it'll be the same thing. So part 3 says, let's use matrix algebra. So we're going to do a little bit of matrix algebra here, just to show that if I have this equation, then this is true. And so remember, with most of our investigations, what we're doing is we're trying to prove a rule at the end, like we're doing essentially a proof through all of these investigations. So these tend not to be what questions look like, but they help us to understand where the rule is coming from or where a formula is coming from. And that's kind of what we're doing here. We're building to a formula that we'll see at the end that has to do with powers of matrices. So it says use matrix algebra to show that if this is true, then so is this. And so for part A, if AP equals PD, which we know to be true, right, if my goal is to solve for A, right, like I'm noting here that I want to get A alone on one side, then I'm going to multiply by the inverse of P on the right side, because in order for it to cancel on over here, it needs to be next to the P. And so when I do that, I get A times the identity matrix, right? P times its inverse is the identity matrix, and this is P, D, P inverse. And so then we can see anything times the identity matrix is itself. So the left side is A, and then we have P, D, P inverse. Right, so we've proven that that's true, that I can transform this into this down here. So then it says use the result in part A to show that A to the third is this. And so let's take a look at what A to the third would look like. So A we've now defined as this thing that I just underlined. And so it's PDP to the -1 to the third, right? Because that's what A represents. And so if I actually write it out, it's PDP times PDP inverse times PDP inverse. And this is all multiplication, right? So we're allowed to regroup things. And you'll see if I regroup some of these um, terms that have p and p inverse that are next to each other, right? Those things are going to cancel. If I have the inverse and it's next to its original matrix, those things become the identity matrix. So I could say it's PD times the inverse of P times P times D times the inverse of P times P times D times the inverse of P. So what I've done is these things that I'm about to highlight, right, represent that and those two. And the reason I've done that is because now what's in the brackets down in the most recent step, this step right here, those are going to turn into the identity matrix, right? This would be P times D times the identity matrix, which means it kind of goes away. So we could say it's times the identity matrix times D times the identity matrix times D times P inverse. And so now we kind of see that we have, this is going to equal P times D times D times D times P inverse, right? There's three of them, 1, 2, 3, which is the same thing as P, D to the third times the inverse of P. All right, so what we're noticing here is if I create this diagonal matrix D, and I want to find like a to the third up here, I can take P, the eigenvector matrix, and the inverse of the eigenvector matrix, and multiply it by whatever that diagonal matrix made up of the eigenvalues is raised to whatever power I'm looking at. So in this case, it was 3. Right? In the first case we looked at, it was 1. And so we're going to try to generalize this eventually in a little bit. So it says for the value d given in question 2, find the value of d to the third. Right, so d was this diagonal matrix, which was negative 1, 0, 0, 8. And so if we want to find d to the third, well, we can put that in the calculator. And if we do that, right, we'll notice we get negative 1, 0, 0, and 512. And so this, remember, this represents our diagonal matrix. Okay, that's why it's the letter D. And it's made up of our eigenvalues, right? Our eigenvalues are in that diagonal. So it says, can you generalize the result for d to the n, right? So in general, what are we noticing? If I raised it to the third, what happened was the zeros stayed the same, right? Those didn't change. And I just raised each term to the third. That's what happened when I multiplied a diagonal matrix by itself 3 times. And so negative 1 to the n would be my result here, whatever n is. And then this would be 8 to the n. Right, so generalizing this is what we're going to work our way up to. So we've kind of looked at how do I generalize the diagonal matrix, and now we kind of want to generalize the whole thing, this kind of thing, which will eventually generalize there in part B. So it says determine a cubed by finding this. So we could find a cubed by just saying, you know, A was this original matrix, raise it to the third in the calculator, but it says by finding this. And then we'll verify our results using the calculator. So for part A, right, we're going to say that it is P was 1, 2, 1, negative 1 from above, right? It defined P for us right here. Right? And so then the diagonal matrix to the third. So the diagonal matrix was 1, 0, 0, 8, and that's to the third. And then we have to find the inverse of P, right? So we need to take 1, 1, 2, negative 1 to find its inverse. And so let's do this. We can do it kind of roughly by hand to see what's happening, but this matrix would stay the same. Right? This matrix would stay the same. Raising this one to the third, well, we already saw what would happen to that. We did it in part 4. So it would be negative 1, 0, 0, and what was it? 512. And then finding the inverse of this one, right? This is where we have to remember our inverse rules, but also this is in your formula booklet. I switch the A and B values, so negative 1 and 1, those switch places. And then B and C get the opposite value that they were. but then I have to multiply by 1 over AD minus BC, right, the determinant. And so the determinant of this one is 1 times negative 1 minus 1 times 2, which is negative 3. So 1 over negative 3 is this kind of constant that I'm going to multiply that last thing by. And I can just leave it outside for now. Um, and so this is where we could say, well, let's multiply this and this, and then multiply it by this, and then we can divide everything by negative 3. And so if we do that, we'll see we get a to the third is going to be 341, negative 171, negative 342, and 170. Right, and we could confirm that in the calculator. We could just say, hey, let's take our a value, whatever our a value was, which we got from the very beginning. Right, let's take our a value up here. Let's raise it to the third, and you'll see you get the same thing as this. Right, so we can confirm it that way. What we want to do is now find a general rule or a general idea for what is a to the n. Right, so our a matrix was, I forgot, 5, negative 3, negative 2, negative 6, 2. 5, negative 3, negative 6, 2. We want to find a general rule for what a to the n would look like. And so we need a couple things for that. We need our P matrix, which we know to be 1, 2, 1, negative 1. Remember, that's our eigenvectors. We need our diagonal matrix, right, which is our eigenvalues in the diagonal there. And we need the inverse of P, right, which is P inverse. We kind of found in the last part. We know that to be this thing, right, 1/3, negative 1/3 times that stuff, right? So negative 1, negative 1, negative 2, 1 times negative 1/3. Right? I'm not putting it inside because then I'm dealing with fractions, and I'd rather leave it outside and just multiply it in at the end. So let's now take a look at what a to the n would look like. It would be p times d to the n times p to the negative 1, or the inverse of p. And so we can put those things into what we have. So it would be 1, 2, 1, negative 1, times d, negative 1, 0, 0, 8, to the n, times negative 1, negative 1, negative 2, 1, times 1/3. Sorry, negative 1/3, negative there. Right, that thing on the end is a constant, right? It's just a scalar. We're just multiplying that last matrix by negative 1/3. So let's distribute our n in. We've kind of already talked about what that would look like. And it would be negative 1 to the n. It would be 0. It would stay 0. And then it would be 8 to the n. And then times this other stuff. And 1. And negative 1/3. And so now let's actually do that multiplication, right? Let's do that matrix multiplication. I'm going to multiply the first two matrices together, right? The furthest left ones. So it will be 1 times negative 1 to the n, which is negative 1 to the n, plus 1 times 0, which is just 0. So I'm not going to write that. So now to find the second entry, it's row 1 times column 2. So 1 times 0, which is 0, and then 1 times 8 to the n. So the second one is just 8 to the n. And then to find the entry down here, it's the second row times the first column. So 2 times negative 1 to the n, plus negative 1 times 0, which is 0. And then the last one is row 2 times column 1. So 2 times 0, which is 0. And then negative 1 times 8 to the n. So it's negative 8 to the n. And so that's times our negative 1, negative 1, negative 2, 1, times our negative 1/3. So now we want to multiply the next two matrices together. Right? I have this 2 by 2 and this 2 by 2, and then I have that times negative 1/3 on the end, because I just don't want to deal with fractions right now. So let's multiply those two together. And so what would happen is I would get this times this plus this times this. So let's combine those to make our first term. So negative 1 to the n times negative 1 is actually negative 1 to the n plus 1, right? Because it's negative 1 times negative 1 to the n. Well, that's just an extra negative 1. So to combine it into 1, it's negative n plus 1. And that's going to be plus. Well, it'll end up being minus because it's negative 2 times that stuff. So minus 2 times 8 to the n. That's our first term. And then I'm going to do row 1 times column 2 to find this entry over here. So row 1 times column 2 would be, again, negative, or sorry, it would be, this one's positive. So it would be row 1, column 2, yeah, it would be negative 1 n plus 1 because of that same thing, right? It's negative 1 to the n times negative 1, right? Which that has the 1 there. If I combine them into a single one, it's negative 1 to the n plus 1, that same thing that we talked about before. And then it would be plus, because it's positive, 8 to the n. And then now I need to figure out my second row. So it would be row 2 times column 1, which will be 2 times negative 1 to the n plus 1, plus, and this time it's going to be plus because it's negative and a negative, so plus 2 times 8 to the n. And then my last entry, right, row 2, column 2, will be 2 times negative 1 to the n plus 1, because it's this times this, right? And so negative n plus 1. And then it's going to be a minus this time, minus 8 to the n. And that still times our negative 1/3. Right, so this is kind of the general rule. If I want to find a to the n, if I want to find a to the 100th, I can plug in 100 for n into this matrix, then multiply it all by negative 1/3, and I'll get my result. Right, a general form for finding that, only using eigenvalues and eigenvectors. That's kind of what we just figured out. And we can always verify it by saying, if I want to know what a to the 100th is, right, I'll just plug in a to the 100th in the calculator. But this is algebraically how we can figure it out using eigenvalues and eigenvectors. So what that leads us to is kind of the more important thing. Part of this part down here, which we'll talk about in a second, shows up in your formula booklet. But an important thing to notice is that if we have this matrix here, A, B, C, D, a 2 by 2 matrix, where real number entries, they have distinct eigenvalues. So they have different eigenvalues where we have 1 and 2 different eigenvalues there. Then we say that A is diagonalizable, tough word to say, and thus can be written as this, where P is so P represents the eigenvectors in columns, which is what we looked at before, right? It's one eigenvector next to the other eigenvector, and that's what this is saying. And then that D is the eigenvalues in what is often called the leading diagonal, which is the one that goes from left to right, like that, right? We have the leading diagonal. So it says, let A be a diagonalizable 2 by 2 matrix expressed in the form A equals P times D times the inverse of P, then the power of A, and this is what we kind of proved in the last one, the powers of A can be represented with this. So this is what appears in your formula booklet. Right, and it's just showing that if you find eigenvalues and eigenvectors, you can also find powers of different matrices. So if I want to find the matrix to the fifth, and I know the eigenvalue and eigenvector, I can find it that way as well. So we're going to go through an example, and we'll take a look at how we would kind of use that formula booklet formula that's up there. So the first part says find eigenvalues and eigenvectors for this one. And so we have this matrix A is 1, 2, 3, 0. And so if I want to find the eigenvalues, remember it's the determinant of the matrix, and that should equal 0. And so, sorry, not quite the determinant. I'm forgetting my variables there, my representations of the eigenvalues. So it's 1 minus lambda, 2, 3, and 0 minus lambda. The determinant of that needs to equal 0. And so that, if I write that out, is 1 minus lambda times 0 minus lambda minus 2 times 3 equals 0. And so at this point, we can say, hey, let's go put that in the calculator, and let's find the roots in the calculator. And so if I find those roots, I'm going to find my two eigenvalues, right? And so my first eigenvalue, if you take time to go put it in the calculator, you can go check, double check that you know how to do it, is -2. And my second one is 3. Right, so these are my eigenvalues. Found the first part. And so if I want to find the eigenvectors, this is where I have to plug in those eigenvalues, and then I can find the equations that are representative of different types or different specific eigenvectors. So let's look at our first one. If I plug in -2 into the matrix, it would be 1 minus -2, 2, 3, and 0 minus -2 times xy should equal 0, 0. Right, and so that's going to be our first one. So it's really 3, 2, 3, 2, xy equals 0, 0. And so I get 3x plus 2y, that's going to equal 0. And so 2y is -3x, y is -3 over 2x. And so this is a case where I probably wouldn't choose 1, like an x value of 1, because then I would get out a fraction. What would be a more appropriate x value would be 2, because then I would get two whole numbers. If I plug in 2 to this function for x, my output would be -3. So one eigenvector that would be a good representation would be this, 2, -3. I could use the fraction one, but then the numbers are going to be much harder to work with. So I usually want to choose the smallest whole number values, because we're going to end up doing quite a bit of algebra with it. So that's one of our eigenvectors. And then if I plug in 3 as my eigenvalue into the matrix, so 1 minus 3, 2, 3, and 0 minus 3, times our xy should equal 0, 0. So that's -2, 2, 3, and -3. Xy equals 0, 0. Again, I can choose whichever one I want. I just happen to choosing row 1 times column 1. You could choose row 2 times column 2, and you get the same thing. And so if I do that, I get -2x plus 2y equals 0. 2y is 2x, so y is x. And so the easiest one to choose for that eigenvector would be 1, 1. If I plug in 1 for x, I would get out 1 for y. So these two things are my eigenvectors. Right? My eigenvectors are here and here. So I've done part A, right? I found the eigenvalues and the eigenvectors. And so now I want to find an expression for, right here, a to the n in this form. And so that means I need to find those various things. So part B, I need to figure out what does P represent. And so remember, P is just the eigenvectors. In this case are 2, -3, and 1, 1. And D, right? D is the eigenvalues in the leading diagonal. So eigenvalues right there. Other diagonal is 0, 0. So I have a representation of P and D. So if I want to find a to the n, it's going to be P, which is 2, 1, -3, 1, times D to the n, which is -2, 0, 3, or 0, 0, 3 to the n, times the inverse of this thing. So 2, 1, -3, 1, inverse. All right, so that's answering part B. Find an expression, a to the n, in this form. Done. Found it. Part C says now, let's write that thing as a single matrix. This is where we have to do all that algebra again, right? Kind of showing um, that if I do all this algebra, um, I will get kind of an expression in terms of n's, uh, where I have a value for a to the n. So the first thing I should do is distribute the n, right? Raising a diagonal matrix to n just means raise the leading diagonal values to n. So this one stays the same. My diagonal matrix becomes negative 2 to the n, 0, 0, and 3 to the n. And then I need to find the inverse of this thing. And this is where we just have to remember the definition of an inverse. The a and d values switch, so 1 and 2. And these become the opposite, so negative 1, and then that was a negative 3, so it becomes a positive 3. But then it's also times 1 over AD minus BC. What's AD minus BC? Well, in this case, it's 2 times 1 minus 1 times negative 3. So it ends up being 5. So we know at the end we're going to multiply everything by 1/5, or divide all of our values by 5 when we get to the very end. It can just kind of sit out to the end because it's this constant. If I distribute it in, the numbers would be just a lot harder to work with. So now we have these matrices. We have 3 2x2 matrices. We're going to multiply them. So I'm going to multiply the first 2 matrices together. And so that will give me 2 times negative 2 to the n plus 1 times 0. So that's the first entry. That's done. 1 times 0, I don't need to write. The second entry would be row 1 times column 2, so 2 times 0, plus a 1 times 3 to the n, so this is just 3 to the n. So now I have to do row 2 times column 1, which would be negative 3 times negative 2 to the n, plus 1 times 0, which I don't have to write. And then it would be row 2 times column 2, so negative 3 times 0, which is 0, and 1 times 3 to the n. Right, so that's multiplying the first 2 matrices together. And so now I have to multiply the second 2 matrices together, right? I now only have 2 of them, these 2x2s. I'm going to multiply those 2 together and see what I get. And so this one's going to require a little bit more work because we no longer have zeros. So we just have to keep good track of what we're looking at. So I'm looking at row 1 times column 1. So that would be 2 times negative 2 to the n plus 3 times 3 to the n. Right, which if I have 3 times 3 to the n, what is that really? That's 3 to the n plus 1. So then my next term would be row 1 times column 2. So it would become negative 2 times, because negative 1 times 2. So negative 2 times negative 2 to the n, which again we should recognize is negative 2 to the n plus 1. And so I can write that first part as negative 2 to the n plus 1. And that's going to be plus 2 times 3 to the n. All right, so we finished our first row. We've done the first 2 entries. Row 1 times column 1 gave us that one. And then row 1 times column 2 gave us that one. All right, so we finished those first 2. And now let's take a look at the next one. So now we're in row 2 times column 1. So it would be, in this case, it would be row 2 column 1. So it would be negative 3 times negative 2 to the n plus 3 to the n plus 1, right? Because there's a 3 times the 3 to the n, so 3 to the n plus 1. So now I'm going to do row 2 times column 2. So it would be 3 times negative 2 to the n. That one doesn't change. And then plus a 2 times 3 to the n. All right, so I've finally gotten my representation. Oh, I forgot my 1/5, right? All times 1/5. So that's my representation of a to the n as a single matrix, right? If I want to find out what a to the 100th is, I can plug 100 into that matrix in one thing, and I can find that. And so that's what it kind of asks us to do in part D. So this last part's short. It says, hence write down the value of a to the 4th. Well, a to the 4th would be, let's replace all of those n's with a 4. And so if we do that, you get, take a moment, pause it, put it in the calculator, see what you get. You get 275 130, 195, and 210. And that's still times 1/5. And so then that means a to the fourth equals 55, because I'm just dividing each of those by 5, 26, 39, and 42. And so you can double check this. This way was done by what's called diagonalization of a matrix, and then using the powers. But if we go a to the fourth, that would be the same thing as saying, well, what was our original value of a? It was somewhere 1230. Right? If you take 1230 and you raise it to the fourth, you're going to get this thing. Right? So we're just showing that there's an algebraic way as to why these powers of matrices work. And there's other ways to find them by using these eigenvalues and eigenvectors. So that's where we're going to pause for the notes today. What I'd like you to do with the rest of class is just to take a look at this investigation. All right, see if you can apply it to a real world. We're going to go over this investigation in class, but I really want you to give it a shot with the rest of your class time. And we will finish up these notes and review what was in this video in tomorrow's lesson. See you all tomorrow.